Hello, everyone. We are UCF's 2020 to 2021 RE-RASSOR Black team. I am Michaela Pinter.
I'm Alex Hilligas.
I'm Brandon Clark.
I am Francis Fermo.
And I'm Connor Wick.
Our sponsors and mentors for this project were Mike Conroy, Kurt Lute, Ron Marrero, and Tiger Saxa.
So before we dive into our project, I should give a brief history about what the RE-RASSOR even is. It is a regolith advanced surface systems operations robot. It was designed at SwampWorks at Kennedy Space Center. Pretty much it's just a rover that can mine regolith, which is an example of regolith is something like lunar soil. It can mine ice, which has been found on the lunar surface. It can also construct robots or buildings rather for something like a landing pad on the moon, and can also handle load and transport load in between lunar bases.
This project started in 2018 with the senior design team that was tasked with creating a simulation of the rover that NASA has at SwampWorks. And they accomplished that using something called Robot Operating System and a visualization software called Gazebo. Our job this year was to take that simulation and convert it to hardware. So Mike Conroy, our sponsor, his words were make it all work. We just had to put everything together and make all of the algorithms that they wrote in simulation work on hardware.
For our team roles, I am the project manager and the obstacle detection lead. Connor is the path planning lead. Brandon is the hardware interface lead. Alex is the motor integration lead, and Francis is the control interface lead.
So the first thing to talk about is the robotic operating system. ROS is considered a middleware system, and what it does is it sends messages between all the different parts of our robot. So for example, the camera has to send its data to the autonomy code, and that data is sent through ROS to the autonomy code, which then outputs an instruction for the wheels that is also sent over ROS.
The first part to getting a moving robot is having motors. To do this, we chose stepper motors because they move in discrete movements, which allowed very fine control of the robot. We needed a couple layers to translate the messages from ROS into instructions for the motor. So we had an Arduino Mega that would take the message from ROS and figure out exactly which motors needed to turn. And then we had the motor shield that would sit on top of the Arduino Mega, and it would take messages about which motor is supposed to turn and translate those into the electrical signals necessary for the motor.
The most important thing for autonomous navigation is a way to see the surrounding area. So we had the Intel RealSense D435i camera on our rover. This camera has RGB and depth capabilities. We specifically chose this camera for a lot of the software capabilities that it had, but it also had ROS packages that were readily available, so we could integrate with the hardware easily. And this camera helps us with obstacle detection, so it will connect to the physical hardware and output the surroundings that it was seeing, and in that way the software could detect obstacles and tell the motors how to avoid them. This piece of hardware for our rover was the brain of the rover, which was the NVIDIA Jetson Nano. This essentially holds all of the software and ROS and the operating system and essentially everything. This connected to both the Arduino and the camera. To the Arduino, it would send movement instructions, and from the camera, it would receive the data from the surrounding area that the camera would see.
For path planning, we use a simple wedge bug algorithm. Basically, the robot scans out wedges around it, and it tries to move towards its destination. If it finds an obstacle in a wedge, it will try to go into a wedge that does not have an obstacle and continue towards its destination. This lets it navigate around obstacles detected by the obstacle detection systems. The obstacle detection systems allow the rover to navigate around obstacles without colliding, and there was already software existing, and we just needed to connect the camera as stated previously.
So after a discussion of all the hardware, here's a use case diagram of how it all kind of interconnects with each other. So first, in the far left, you'll see that we have a computer connected with a keyboard or an Xbox controller or something like that. And we will communicate with our Nano, with the brain of our rover, via Wi-Fi through an SSH connection. That Nano is also powered with a battery as well. So on the Nano, we will obviously need a Wi-Fi receiver so that it can be connected to a network, but it'll also have the camera connected to it via a USB cable. Now from the Nano, it will send the algorithms and kind of the wheel instructions to the Arduino Mega. And what the Arduino Mega does is it takes those instructions and translates it into machine code that gets sent to the motor shield. Then that motor shield will take those machine instructions and then translate that into electrical pulses to turn the stepper motors themselves.
This is our autonomy demo. We have the rover hooked up to a laptop right now, and what I'm going to do is I'm going to speed it up until it encounters an obstacle. So we're at the first obstacle. The process for it going around an obstacle is actually quite slow. So first it turns to the right side, then it turns to the left to judge which side is better for going around the obstacle. And then it turns back in the direction it thought was better, and it slowly turns back to the obstacle at set degree increments, determining which direction is actually best to go around the obstacle, and it picks a very conservative one that makes a wide berth around it. So here it picks the best angle and it heads off.
So for RE-RASSOR, we also wanted manual control of our rover using a multitude of controller hardware. So here you can see me controlling the rover with a keyboard through a wireless network, and this is all done wirelessly. Next, you're going to see me switch to a gamepad controller. This is a PS4 controller. This is all connected through a wireless network. The laptop and the rover itself is connected through a network that is all communicating with each other. Lastly, you will see me use the Android app that was actually created by a previous senior design team. Again, this is all completely wireless. This is also using the RE-RASSOR software from previous senior design teams. So here is a quick demo of just all three controlling hardware that you can use with RE-RASSOR.
So one of the challenges we faced over this last year was having to do all of our meetings virtually. Our group decided to meet weekly with each other, as well as weekly meetings with our sponsor, a NASA software engineer, and sometimes with the original creators and maintainers of the RE-RASSOR software.
We chose this project because all of us have a huge interest in aerospace and NASA. We got an opportunity to learn about robotics and simulation software, and we loved the space environment of the project. Additionally, some of us had interest in other fields like object detection, computer vision, and artificial intelligence.
So we had two main challenges that we faced throughout the year. The first challenge was that because we were using hardware, we needed a budget to pay for this hardware. That budget and the approval for the funding took a bit of time. To be exact, it took about one entire semester. So the solution that some of us had to come up with is that we paid out of pocket to buy some of this hardware ourselves, like a stepper motor or the Arduino Mega, so that we can do our own testing. Another issue that we ran into very late during senior design was actually in the second semester of senior design 2. We kind of came to the conclusion that 3D parts that we were supposed to have been printed were not going to be completed in time. This is from another design group that had designed the rover, the 3D parts of the rover rather. So what we decided to do is that we should probably, to have a demo ready RE-RASSOR, is we need to design our own rover. And as you can see in the picture in the top right there, that's kind of what we came up with, just so that we can have something that's legible and in our hands, so that we can have it be demo ready.
So some of the motivations that we had during this project was being able to see the physical rover working on its own and behaving like the simulation, and really having to have the physical rover isn't something most computer science senior design teams get. Another big motivation was knowing that someday there will be a version of this rover on the moon building a lunar landing pad.
Through our weekly meetings with engineers at NASA and Florida Space Institute, we had a constant feedback loop with our sponsors and those people. So this kind of prevented us from getting off track, and a lot of times we would come to them very early on with hardware suggestions, and they would give us a thumbs up or thumbs down. And that made the feedback process really simple because we had almost instant feedback on our decisions.
Some of the biggest lessons that all of us learned from this project were, the first one is that interdependencies are really common in real world projects, which is what we learned from talking with our sponsors and mentors. So the real thing that they taught us through this is that you can't let other issues cause you to stop your own project. You can't just wait for someone else to solve this problem. You have to make a solution yourself sometimes. And the other biggest lesson is that it's really important to have a base understanding of an existing project before you try to jump in and add or change things to it, because then down the line, you're going to be more confused than you were if you just took a couple of, days or weeks or months to actually understand what you were getting yourself into from the get-go. So that is our project, and that was our presentation. Thank you all for listening and watching.
Thank you.